hanging in there? I always appreciate you being here on time. Thank you. Right? It's hard to get up and get out of a nice warm bed into the cold, nasty world to come and get beat up by physics, right? But I am glad you're always here on time. Thank you. All right, tomorrow, tomorrow's lab 7, centrifugal acceleration. I'm hoping that we can do the promised field trip tomorrow. What I need is a certain place on campus to be dry. So the rain has been making that a little bit problematic. So I'll check it. I checked it this morning. It was too wet, and so I'll check it tomorrow. See if it's dried up enough. But we'll get there. Okay, we'll do the example on tomorrow. Hopefully tomorrow. If not, we'll try to squeeze it in Monday or something like that. So just remember, it would be advantageous to have shoes that you can run in. Right? Not everybody needs them, but few people do. All right. I am doing examples, like from here until the exam, right? It's nothing but example city of conservation of energy. You can use what I'm teaching you about conservation of energy on chapter 7 and chapter 8. Okay, just because it's chapter 7 doesn't mean you're not allowed to use it. It works great. Okay. In fact, some of the chapter 7 problems can be a little bit difficult if you try to do them with only what they tell you in chapter 7. They're possible, but they're just better when you just do the entire conservation of energy. So we did the free fall example, okay, and we will be getting to air resistance today. But let's start with everybody's favorite armadillo or penguin or insert object here, right? Anything that happens to be sliding down a hill. And these shapes you find everywhere. You'll see inclined planes over and over and over again in everything you do. Well, okay, maybe not you electrical engineers. They have worse things to deal with. All right, let's put our. It wasn't was it aardvark? Armadillo? What was it? Aardvark. Thank you. Let's put our aardvark on a hill with friction. So we can do the whole enchilada here, right? And now, with conservation of energy, can we find acceleration? Two things conservation of energy could care less about. What are they? Acceleration and time, right? If you're looking for those things, you got to go find a different toolbox. So we can't find the acceleration. But what we can do with conservation of energy, we can ask the question, how fast is the aardvark going when it gets to the bottom of the hill? So let's just sketch out really quickly what you'd have to do if we didn't have conservation of energy to do this. So to find out how fast the aardvark's going, if it starts at rest, how fast is it going at the bottom of the hill? What would you have to do? We'd have to do free body diagram, Newton's second law, all in an attempt to find what? What's the key piece of information we need to be able to use to do kinematics? The acceleration. Right? If we don't know what the acceleration of the object is, it makes it really hard to do the kinematic equation. So we'd have to do a full Newton's second law setup, right? And then we would have to go take kinematics into account and do the two-dimensional tilted problem, right? So that's two toolboxes coming together. Let's see if we can do this all in one toolbox. Again, all we want to know is how fast the aardvark's going, right? When it gets to the bottom of the hill. So what are some things that we may need to know? We might need to know the angle that the screen is not working. Right? Thank you. I'm glad somebody told me. I could have been in 20, 30 minutes. What technical nightmare has happened now? Not that one. Not that one. All right, let's try again. All right, that worked. That refuses to work. How exciting. Let's back out. Always try a reboot. That. And now, nope. Oh, we're gonna have to do this the old-fashioned way? Wouldn't that be fun? Come on. Now it refuses to do anything. Haha. Now you're seeing stuff, right? Going over here. All right. I'm going to chalk that one up to the aardvark. It obviously didn't want to play nice. All right. So I just established that we'd have to use two different toolboxes, but let's try to do this from point of view of energy. We're going to need an angle, and I brought numbers for you today. I was feeling nice, right? Okay, let's say that the hill is tilted at 40 degrees, okay? Let's also, let's say that we know that the aardvark slides a distance of 100 meters down the hill. Now, with that distance, I'm not talking about like the vertical height or the horizontal height. I'm talking about like the distance it slides on the incline of the hill, right? So that distance would be like from here to here, right? All the way down the hill. And then I said we're going to solve for velocity, right? So we're given that the coefficient of friction is 0.32 between the aardvark and the hill. So let's go out and let's find how fast. If the aardvark starts with 0, right, starts at rest, let's find out how fast it's going. Okay, so visualization. 3 things that are really important for us to define. What are they? For conservation of energy. This is what happens after 2 days, right? Initial, final, and 0. Where's the 0 for gravitational potential energy? Let's tackle the last one first. Where do I always put it? At the lowest point in the problem, right? Might not be where the object gets to, but it's sort of like the lowest reference point in the problem. Okay. Initial. Where do you want to put your initial point? where it starts, right? So, like where you know something, okay? And then you want to put the final point at a spot where you're trying to find something. There's usually some unknown thing at the final point that you are looking for. In this case, it is our velocity, right? How fast is it going at the bottom of the hill? And energy, it really just cares about an initial and final. Things can be happening in between, and energy can take care of that, but it focuses on the initial and final. Okay, so what's our strategy step? What do we do to get kind of started beyond the visualization? Yeah, you just write the equation. You start here. It's always the same start, okay? Work other plus energy initial equals energy final. And now you start applying physics and concepts into, what do I have work other? What are my initial energies? What are my final energies? That sort of stuff. Let's start with initial energy. Does the aardvark have any kinetic energy to begin with? Why not? It's not moving, okay? So kinetic energy initial, that one's 0. All right. Any potential energy of any kind? We need to be thinking about springs and gravity. Yes, what kind? Gravity, right? Gravitational potential energy. So we'll put in potential energy initial. And since there's no springs, I'm not going to worry about springs anymore, right? Okay. At the bottom. Any kinetic energy? Yeah, how do you know? It's moving down there, right? We're trying to find out how fast it's going down there, so it better have some kind of kinetic energy. And what about potential energy? Any potential energy at the bottom? No spring down there. And what would gravitational potential energy be if the aardvark makes it to the bottom of the hill? 0. Why? Because that's where we put 0. Right? Always have a reason for being able to say something is 0, right? And in this case, the final potential energy is 0 because we put 0 there. All right. Well, that leaves the work other term. So is there a force besides gravity and springs that is acting on the aardvark as it slides down the hill? Yeah, friction, right? Okay. So friction is going to be the thing that always finds itself into work other. Okay? If friction's involved, you're guaranteed to have work other going on here. Okay? So we do have the work done by friction. And I just write work and then just some sort of subscript to tell me, and in my next step, I'll try to start figuring out what that work is. We know what mathematically how to write out potential energy initial. What would it be? It's mgh, okay? What h? What is h? It's not the distance down the hill. It's not the 100 meters. It's the vertical height, okay? It's the completely straight up height, right, that the aardvark starts at. Now, we weren't given that, were we? Can we find it? Yeah, unfortunately, yes. And why is it unfortunately? Trig. Right? Okay, we know the hypotenuse, we know the angle, and we're looking for the side that's not touching the angle, so we're going to use sine or cosine? Sine. Right? So MGH is going to become MGD sine theta, isn't it? In this triangle I have over here. Okay. The side I want is not touching the angle, and I know the hypotenuse, so I know I'm going to use sine. All right, what will we write down for the final kinetic energy? Like mathematically. It starts with a 1/2. mv squared, and that doesn't change. All right, and then we have this work due to the friction that's in the problem. So we know that work is force times distance, or we should be very careful, the dot product, right, between the force and the direction that the object is moving. What do we know about objects that slide? What kind of friction is it? It's kinetic friction. And what direction does kinetic friction always act? opposite the direction it's going. So what kind of work does kinetic friction always do? It's always negative work. So I'm going to go ahead and just write in here minus F times D. Now in doing so, right, I didn't write down F dot product D with vectors on it. I didn't write FD cosine theta, right? I did physics. I said, look, if we can draw the free body diagram, but we know that that friction is going to be acting up the slope in the plane of the slope, and we know that the direction that the aardvark is going is down the slope, so negative work. All right. So now, do I know what that friction is? What? I heard it. Fun. Right? Right? It's just so much fun. If you say it enough, you'll live the lie. So we know that this is mu times n times d. Again, we want to solve this for the v that's sitting over there, right? Look at the mgd sine theta. What is that? Is that something we know or something we don't know? We need the mass. You're going to hurt me, aren't you? Oh, no. Not yet. You're not going to hurt me yet. Never mind. It's going to be okay. We don't know the m, but we know the g and the d and the sine theta, don't we? Okay, so we got to figure out the mass, but we also need to figure out that normal force. The normal force has snuck in, hasn't it? So how are we going to find the normal force? This is where you might hurt me a little bit. This is where we do have to jump back into chapters 5 and 6. Yeah, because we need to take a look and be careful. Inclines are nasty, right? Okay, there's my normal force. There's my weight. Here's my friction acting up the slope. And we need to find out what the normal force is. Well, we know, right, when we break up the components of mg, that there's a component that points opposite the normal force, isn't there? So what is that component? Mg cosine theta. So that's true if there are no other forces acting in the vertical direction on the object. Let me be pretty clear here, right? And give you a what if, okay? So here's an inclined plane, here's an object on the plane. We know that the normal force goes like that. We know that the weight goes like that. If there's friction or any other force that's operating along the plane, that's not going to have any effect on the normal force. It's perfectly perpendicular to the normal force, nothing's going to go on. So there could be tensions, right? There could be people pulling, there could be all kinds of things going on along the surface. Not going to do anything in normal force, okay? But what if something came in and pushed opposite the normal force? What's going to happen to the normal force if something's pushing into the hill? It's going to increase, isn't it? Okay, so not only are we going to have mg cosine theta, our normal force is going to be equal to mg cosine theta plus p. You can start at 0 and go n minus mg cos theta minus p, right, for all the directions. But the point is as soon as you get another force that acts in any part of the vertical plane, you have to account for it. So just be careful. Don't always assume that the normal force is equal to mg cosine theta. That's true if there just isn't any other vertical forces. Another example would be if something were like pushing, right? Kind of perfectly horizontal but at an angle to the slope, right? Well, now there are x components of this force, right? And y components of this force. So you'd have to go find components of those, right? And in this case, if that were the angle, then This is the angle, so that would be F cosine theta, right? So when friction's involved, when you are looking for normal forces, the safe thing to do, which is the hard thing to do, but it's still safe, is to fall back on chapter 6, draw the free body diagram, make sure you know what the normal force is. And it doesn't have to be like a strict free body diagram, but you probably want to make sure you know which way you're saying is positive or negative, right? Okay? And don't worry, you don't have to write out Newton's second law, you don't have to go into that algebra jungle. But the free body diagram is still a useful tool, and this is where vectors do sneak their way into energy, right? Because it becomes important to know what the normal force is going to be. Luckily in this problem, there's no other forces, nothing pushing in the aardvark into the hill or whatever, right? Okay. So the only thing I need to worry about in terms of the normal force is mg cosine theta. They're the only things in the vertical plane. So I can go ahead and just write this as mu mg cosine theta times d, just shoving in what the normal force is, right? And then I have mgd sine theta equals 1/2 mv squared. I still don't know what mass is. Why didn't I give you the mass? Cancels out, right? It's in every term now. And so it actually doesn't matter if it's an aardvark or an elephant or a mouse or anything else. Okay? It's going to work, cancel out. So, the first term there, that negative mu g cosine theta d, what is that? It's a number. Do we know all of those numbers? Do we know what mu is? Do we know what g is? Do we know what cosine theta is? Do we know what d is? That's a number, right? Put in my calculator, it's going to be a number. What about gd sine theta? Also a number, right? Whatever it is, don't care. Okay. And then what do I do with the 1/2? Right? I can just start solving for v squared here. This is going to be 2, right? And I can hear my math teacher yelling at me. I should factor out the g and the d, leaving behind, and my math teacher would want me to reverse everything, sine theta minus mu cosine theta. I did sort of like do 3 or 4 math steps right there, right? Okay, equals v squared. And then how do I get rid of the v squared, the squared thing? Take the square root, 2gd sine theta minus mu cosine theta. And I've now solved this for any object on the surface, on any planet, for any distance. Right? Not the specific case of the aardvark on the Earth, but this works everywhere, right? Which is nice. Okay. When I did this, when I actually put in all these numbers, the type calculator, I got 28 meters per second. I have no idea if that's correct. But I'm going to go with it because it's what's in my head. Don't much care because, I'm not an engineer. I don't need to know the numbers. Now, if you're on the homework, okay, and they don't give you the mass, that's a little bit of a hint. It's a hint that what might happen. It may cancel out. If it's the exam and you got a question that doesn't have mass in it, well, now what do you know? I either made a mistake in writing the exam, okay, or you don't need it. So you'll come up and ask me, hey, Mr. Balogh, you didn't give the mask for this one. And I'll either look at you and smile under my mask, right, okay, and say, well, you don't need it, right? In which case you'll go back to your seat destroyed because, of course, you're thinking, yes, I do need it, Mr. Balogh, make my life much easier. Or I'll look at you in shocked horror and realize I forgot to give you the mask, and I'll go find it and put it on the board. Right? So always ask. In my class, always ask, right? In real life, right, you're working on the high-speed rail or whatever it is you're working on, people aren't going to hide things from you that you need to know, right? That's sort of that's a trick in textbooks and things like that. But we are trying to sort of hint sometimes in these problems that, hey, If you do it symbolically, you'll see things will cancel out and you won't need them, right? And they become unimportant or don't have an effect on the problem. Which to me always feels a little bit like magic. Like the mass really doesn't matter if this is an elephant or aardvark or a mouse or anything, and the answer is no. I mean, the shape of things does determine their coefficients of friction, but we're not going to get into that particular jungle in this class. All right. Let's see. Is this thing still going to work? Amazing. I'm very, scared of my technology this morning. No, I'm not. I always win. Got to adopt that. I worked in technical support for 6 years, paid my way through college, and one of the things you had to do with a computer was establish your mastery over it from the get-go, right? When I walked into I worked at my school, and I would do faculty support for computers, and the faculty call you up, tell them their computer's broken. If you walked into the room and looked at the computer and said, I win, you don't, it would instantly fix itself. Faculty would be mad, right? Because they said, well, it wasn't working before you got here, and well, now it is. So I walk out of the room, it's going to stop working. All right, this problem, I've been mean, and I haven't given you any numbers. Anything in quotes, you can pretend is a number that you've been given. But I do want to, again, really I'm trying to sell you on this symbolic thing, right? Doing it with symbols gives you legs and takes you places you never thought you could be. So, the mass is given, okay? The spring constant is given. Ooh, there's a spring in this problem, so what do you know instantly? Potential energy of a spring somehow, some way, right? Okay. Height, okay? They want us to solve for the height. So H is in quotes, but it's not like a given thing, right? It's the thing they're asking us to find. And they do tell us how far the spring has been compressed. So got to have a visualization here, okay? And I couldn't find the launcher that I wanted to find this morning, so I'll use my thing here, right? Okay, but this is kind of an old thing. I'm not sure that do circuses even exist anymore?
Yeah, I've seen it.
Yeah, they do? Okay.
They're a lot less mud.
Yeah, are allowed to have any animals in them anymore? Circuses got a bad rap for animal cruelty and all that kind of stuff. So, but anyway, one of the stunts that they would do sometimes in a circus, and I still think I could probably pull something up on YouTube now that I think about it, right? Is you put somebody into a cannon, right? And the cannon has like a spring or some charge or something, and it launches, right? The object out, okay? So we have this case where we've got this clown, right, loaded into this cannon. They don't tell me anything other than it's powered by a spring. So I'm going to assume that like there's no friction between the clown and the cannon as this thing launches, right? Okay. So, but they want to find, right, the height above the cannon's like exit. Okay. How high does the clown go? Don't try this at home, by the way. Don't ever shoot yourself out of a cannon straight up. Right? You always want to have some angle. What?
Sideways is okay.
Sideways is okay, but you always want to have some angle, okay, so that you can land in the net. Okay? So we're gonna find the height from tip up to there, right? So here's a visualization for us. Draw this picture as best I can. So I've got this cannon, right? And I've got like the spring right here, right? I've got the clown. It's a big cannon. And like the spring is gonna like stretch out, right? To that point. And the clown will start flying, right? Until the clown gets to maximum height. Okay, and then we're not gonna worry about the clown anymore after that. I want you to know that no springs were harmed in the creation. All right, so, okay. 3 things that we need to establish. What are they? Always a part of your visualization, 3 things. Where 0 is, initial and final. This is a choose your own adventure. What do you want to do first? Zeros? Okay, so 0 for gravitational potential energy. Where does that go? The lowest point in the problem, which in this case, right, is when the spring is fully compressed. And then, what about 0 for the spring? Is the 0 for the spring the same as the 0 for gravitational potential energy? It isn't. Because 0 for springs is not something you are allowed to choose. It's always picked for you. Where is the stretch of a spring 0? Do you remember? Where does the spring need to be? Fully compressed, fully stretched, or at equilibrium for us to be at 0?
Equilibrium.
It's the equilibrium point of the spring. It's the relaxed, resting, uncompressed, unstretched location of the spring. And in this problem, that 0 is right there. I'm not told otherwise. So I will assume, right, that once the spring has stopped pushing on the cloud, that it's gotten to its equilibrium point. Are you allowed to have two different zeros like this? Yeah. The 0 for the spring, you're not allowed to choose where that is. It has to be at the resting point of the spring. But the 0 for gravitational potential energy, you are allowed to pick. And it can go anywhere you want. Again, I like picking it at the lowest problem. If you want to put 0 for gravitational potential energy at the same place as the spring, you can do that. That's fine. But what do you have to be careful of if you do that? The cloud starts below 0, right? So any distance it starts below that 0, you're going to have negative gravitational potential energy. Personally, there's two things that scare me. Quadratic equations and negative signs, right? They've always had it out for me. It's not that I don't like them, it's just they don't like me. And I always make mistakes when I'm doing either of those things. So if I can build into my method a way to avoid making minus sign errors, by golly, I'm going to run with it, right? Which is why I gave you my rule of thumb that says, you know what, just stick the 0 for gravitational potential energy as low as it can go. When you have a choice, right, stick it as low in the problem as you can go, and then that means basically anything above it's going to be positive energy, and I don't have to worry about minus sign. So that's why I kind of teach you the things that I teach you, right? It's because I've survived through it, and I'm hoping to help you survive through it as well. So let's keep the zeros different. It's going to be okay. It's going to be okay. All right, we need to establish initial, final as well. So where are we going to put the final? Max height? Why are we going to put it at max height? We know something about what's going on up there. What's going on up there? Comes to a stop? Why does it come to a stop? Because the vertical velocity of anything at maximum height is 0, right? Okay. We also want to find the height above the exit of the cannon, right? And that point is the point where we could measure a distance from, right? So again, just to be clear, right? Our height is measured from here to here. Our D, the compression of the spring, is measured between those 2 points. So it can be helpful to put those on the diagram. All right, where are we going to put initial? I'm going to put it where the cloud starts. Again, sometimes there's this temptation to put it like, do an initial where the cloud starts and a final right as it exits the cannon, and then do another initial there, like break up the problem, but we don't have to do that. When it comes to energy can handle the whole thing. You gotta have to trust it. Trust yourself to be able to tell energy the right things. Trust it to have your back when it comes to finding everything. All right. And then again, our strategy always starts with this equation. If you're stuck, write that equation down. It'll start your brain going, and then start asking questions. And what are the questions you're asking this equation right now? What kind, is there kinetic? Is there potential at the initial and final points? Maybe you're scared of work other, don't understand what to do with that. Leave it, right? It'll come back, right? Okay. Let's just dig into it. What do you want to dig into first? The spring. Yeah. Okay. So let's target energy initial, energy final, because that's really where the spring is going to show up. Okay. So at the initial point, what kinds of energy exist at the initial point? What kind of potential? Spring potential energy. Why is it spring potential energy and nothing else? Is the spring compressed or stretched down there at the initial point? It's compressed. So you know that there's going to be 1/2 K and it's x squared, right? But in this case, d squared. Here, let me back up. Probably better to just write notes. There is going to be potential energy in the spring initial. What about potential energy gravity initial? Is there any gravitational potential energy at the initial point? Why not? Because we put 0 there, right? That's where 0 is for gravitational potential energy. Okay. But there is spring potential energy because we're not at the 0 for the spring at the initial point. Is there any kinetic energy down there? Why not? Not moving. Energy just, I don't know. Energy always feels more concrete to me. Is it moving? Yes or no? Right? Is it at 0? Yes or no? Right? With Newton's laws and kinematics, I'm sometimes left guessing, do I need a minus sign here? I mean, it is concrete, but the concreteness only comes with experience. This one just like, yes, no, yes, no, yes, no. It's a great algorithm. All right. At the final point, we ask all the same questions. It's just we put finals on them, right? Gravitational final and spring final. Okay. Is there any kinetic energy up at the final point? No? Why not? Not because no. Not moving, right? It's at maximum height, so it's not moving. No, we don't care. If you don't care about it, that's philosophy. Maybe art. Is there any gravitational potential energy at the final point? Another way to ask that is it at 0 for gravitational potential energy? The answer is no. So there must be some gravitation. And then up at the final point, is there any spring that is compressed or stretched? No springs up there. So that one thankfully goes to 0. Okay. And then, of course, we've got this work other term that we've got to deal with. So when you're asking, so first question to ask yourself, is there any friction? If there's friction in the problem, then you're going to have work other. Okay? Is there any friction in this problem? No. Are there any extra forces that are pushing or pulling? That's not a spring, then it's not gravity. We're ignoring our resistance still. Why am I holding off on that one? So, always ask that question, right? Are there any forces that aren't gravity or a spring that I need to take into account in this problem? There's no friction here, no other forces. The clown doesn't have a jetpack or parachute or anything else. Nothing else is pushing or pulling on the clown. So my work other in this case is going to be 0. If you're going to make mistakes, this is probably the mistake where you're going to make the mistake, right? Is forgetting to include something in work other or getting the wrong sign on it or something like that. I mean, granted, you're going to make mistakes in the algebra and that too, but you're working through those. You'll get those out of your system eventually. Hopefully before the exam. All right, so what do I write down for potential energy of a spring? Kind of gave this one away already. 1/2 K x squared, but how far is the spring compressed in our problem? The distance d, so Instead of x, we'll use d. All right, and then that equals, and then on this side, I have what? What do I put? Okay. MGH, that's the mathematical form, but what is the h in this problem? What's the total height above the 0 point? It's h plus d. So h as a concept, right? The vertical height that the object goes or the vertical height it falls. But in this problem, h means something very specific, doesn't it? It means the height above the exit of the cannon. So it's MGH, but I've got to make sure that I am consistent with my initial and final choices, right? H plus D. To get that full distance, right? It's the final gravitational potential energy with respect to the 0 that we picked down there at the bottom. Okay. What am I looking for? Height. Oh, h. Okay. Now we do algebra, right? Divide both sides by mg. Subtract the d. Answer done. Solve for any mass clown with any spring, compress the distance d on any planet with little g. In case you wanted to take your circus to the moon.
That's only for vertical, right?
This is only for vertical. Yeah. No angles in this one. Can't really recycle that, right, into anything else. How you doing? Where are you confused? Where are you uncertain? Where are you certain? Are you awake?
Is gravity for these problems not?
Yep. Yeah. And remember, it's never negative 9.8. The negative sign would be attached. It's negative g, and g is always just a number, 9.8, right? So when you see g in these things, you just put in 9.8. What are your feelings about energy like in comparison to the other things that you've learned so far? It's what?
It's just
Different.
different.
Okay. Sometimes students tell me that it feels too easy to be true. Like, wait a second, Mr. Balogh, I must be doing this wrong. Like, it's too quick, it's too fast, it's too, right? Don't doubt yourself, okay? I know you're new to it, right? And I've been around it a long time, and it's always my go-to because it's fast and easy. I can do it really quick. But that doesn't necessarily mean you have to think that way. You might like Newton's second law better, right? With all the visualization in it. Everybody does like kinematics because kinematics is the thing you started with. You now know it's easiest, easier than Newton's second law. Right? All right, let's do a quiz. All right. It is time. It's time to introduce air resistance. We've ignored it long enough. Okay. So, skydivers. I've never done it. Looks fun. Is it? My father-in-law is turning 80 next year, and for his 80th birthday wants to go skydiving. Pismo?
Yeah, they have one out there I went to. You can like take you up.
Okay. We were thinking about going to Hollister, but we'll look into the Pismo one too. But we're going to make it a family outing, so either there's going to be tragedy in the extended family, or we're going to have a lot of fun. I've always wanted to do paragliding.
feel like that's worse
Why?
because you're in the air longer.
Yes, exactly. Right? I've always wanted to be a private pilot, but I'm a teacher. I can't afford that. But paragliding to me just sounds. I used to in Yosemite they have hang gliders that go up at Glacier Point, and I grew up there in the summer times, and I would go down and watch the hang gliders jump off the edge of Glacier Point. And man, I've always wanted to fly. Anyway, sidetracked. Skydiving. So, how do parachutes work? They open up and increase what? Air resistance, right? So, the skydiver has air resistance as they fall through the air. In fact, they start falling at 9.8, but the acceleration gets less and less and less till they reach terminal velocity, right? So we know that the acceleration is like constantly changing on the skydiver until they reach terminal velocity. And if we did this with kinematics, that means we'd have to go get integrals to figure all that out. Maybe that's fun for some, but okay. And then we'd have to have a problem where they're at terminal velocity, then figure out where it's at. It's just a mess if you try to do it with any of the other toolboxes. So let's do it with energy and see what happens. So I'm just gonna sketch this out. We know that the total height of the jump, right, is 1,000 meters. Okay, and we also know that like at the 200 meter mark, okay, is where this parachute opens. We also know that while the parachutist is falling, there's a 50 Newton air resistance happening. Okay. On average, this is cheating a lot actually. Does the air resistance change with speed? What do you think? It does. Okay. It changes with speed. It changes with orientation, like how much of the cross-sectional area of the object is hit by the wind. So skydivers can fall faster by like falling feet first or head first. They can fall slower. They can look like flying squirrels if they do those wingsuits. But so we're sort of taking this average, right? We're saying it's constant over that entire time, and that's pretty close to being true. And then the parachute definitely, right, opens quickly, right, has a large acceleration, slowing down associated with it. But we're given these averages. All right, so that's kind of what we know. And what do we need to establish as our visualization always? What are the three things? Zero, initial, final, right? So initial is going to be when they jump out of the plane. Final is going to be at the ground. Why am I picking final at the ground? It's where we want to find something, right? What is the question asking us to find? Part A? How fast are they going when they reach the ground? So I want to put my final or initial point at a place where I'm looking for something. Otherwise, conservation of energy isn't going to help me much, right? So I'm going to put my final button. And then where's zero going to go? Think like Mr. Balogh. Well, don't always think like Mr. Balogh. But in this instance, think like Mr. Balogh. Lowest point in the problem, right down there. And I know there's part of you go, but Mr. Balogh, what about the 200 meters? Okay. Let's see what happens. Work other. Energy initial. Energy final. Is there any work other in this problem? Oh yeah. Woohoo, right? And not only is there one, there's two. Why are there two work others? There's a change in the air resistance. So there will be a work done by the 50 Newton force and a work done by the 3600. I'll just kind of symbolically represent them like that. I haven't written down mathematically what they are. I'm just kind of keeping track that there's going to be two forces doing work in this problem. And it's air resistance, so I know it goes in work other. It's not a spring and it's not gravity. So I'm throwing them into work other. All right. What kind of energy does the skydiver have initially? What kind of potential? Gravity. Any kinetic? Why not? Starts at, hops out of the airplane, starts at 0. All right? When the skydiver reaches the ground, and again, right before the skydiver reaches the ground, because we're trying to find out how fast they're going as they reach the ground. What kind of energy does the skydiver have? Kinetic, because it's moving, right? Any gravitational potential energy down there? That's where we put 0. Any springs down there? Nope. All right, so it looks like maybe we caught everything. Here, you'll notice I didn't write out potential energy, gravity, potential energy, spring, kinetic energy, initial, right? Okay. I'm modeling for you that process that maybe you can do in your head. That's a little bit dangerous because it's harder if you go back to see what assumptions you were making, right? So you may want to write down, if you're writing this, you might write off to the side, no kinetic energy because not moving, right, or whatever. Leave yourself notes so that when you come back to study this, you don't have to do that heavy lifting all over again, right? Past you has got your back, right, for future you. All right, so, and again, those notes could be like potential energy final equals 0 because at 0, right? You could write something like that, right? Kinetic energy initial equals 0 because V naught equals 0, right? You just have all these little notes to yourself off to the side. All right. Okay. Let's. Okay. So, what is the gravitational potential energy? Start with mg height. What height? It's the 1,000-meter height. And why is it the 1,000-meter height? It's the total it's falling, right? Okay. So I wanna keep things in symbols here. I'm gonna call this 1,000 meters. I'm gonna call that the height. And then because I'm not very creative, I'm gonna call D, right? This distance right here. Okay. All right. So I put in mgh because that's the full height from 0. All right, what do I write for kinetic energy final? 1/2 mv squared. All right, now I got to deal with these work others, right? The work that the 50 Newton force does, static or kinetic friction? It's kinetic, right? Sliding through the air, okay? So, what do you automatically know about the sign that goes on that work? Negative work. Okay? Air resistance acting up, object is going down. So it's going to be minus the force due to the 50 Newton force times the distance that the 50 Newton force goes. Plus, we're adding these works up. Talk to me about the work that the parachute does. Also negative work. So why do I have a plus sign in here? I'm adding together all of the works that I have in the problem. Work others like this sum, okay? So you add together all the works. It just so happens that each of the works in this problem are what? Negative works. So you're adding together these negative things. I don't make the rules when it comes to mathematics.
Is your distance 360 or 200?
Well, it's the distance that the 3,600 Newton force acts. That's what I'm trying to sort of... I'm being very bad with my symbols here today. I'm not sure what's wrong with symbols in my brain. So, now I can go ahead and start throwing in my numbers. Maybe. I don't have this example anywhere in my notes. That's exciting. Where did it go? It's not here. I don't know where it is. Get your calculators out. We're probably going to need them. 50. That's the force, right? 50 newtons. And what distance does the 50 Newton force act? It acts for 800 meters. Right? And then I'm going to add on a negative thing here. So negative. The force, the 3,600 Newton force, is 3,600 newtons. And how far did that force act? What distance? 200. Plus mgh. So it's an 80 kilogram skydiver on planet Earth, and the distance is 1,000 meters. 1/2, 80, and then my unknown thing is a v squared. Everything here is a number except this v, right? Maybe it's back here. Huh, it is. I found it. Never mind. So when you solve this for v, you just got saved from having to type stuff in your calculator, right? How many of you spent like too much of your life arguing with your calculator? Trying to get the right syntax in there and all that kind of stuff, right? And some parentheses is off somewhere, and it's all wrong, and y plus is red, and life is bad. And this is why I do symbols. I don't like numbers. Don't like calculators. All right. So when you do this and you solve this, you get. Matter of fact, I'm going to write this over here. V equals 24.5 meters per second. Meters per second. That's like 50, between 50 and 55 miles an hour. Is that a good day? Hitting the ground at 52 point something miles per hour? That is not a good day. That's dead. That's bad. Right? What should this parachutist have done? Opened way sooner than 200 meters? It's like 600 feet off the ground. That doesn't work. So, we're going to do part B, where we're going to help the parachutist figure out when they should. Anyone want to guess? Give you a hint. It's a number bigger than 200. 500? Any other guesses? 550? 1,000? Is Price is right? What's going on? 551? Price is right rules? No gambling on campus. All right. So, what changes in this problem? So the actual height for gravitational potential energy doesn't change, right? The 1,000 meters that we're sticking right there, that doesn't change, right? Okay. What do we know this time? We know the final velocity, so we're not solving for v, right? But can we recycle this thing right here? Would the analysis for the problem stay exactly the same up to that point? Have we changed the work other in the problem? Have we changed the height that they're leaving the airplane? None of that's changed, right? So, what we now don't know, okay, is where this point happens to be. So, we have this unknown d, don't we? So how do we know what this part is? It's 1,000 minus d. Right? If they had to open at 400 meters, let's say, then how far did they fall before the 400 meters? 600 meters, right? So this, whatever d is, okay, this distance is going to be 1,000 minus d. So I can pull this down. I can say, okay, I know that my force is 50, but my distance now that the 50 Newton force acts is 1,000 minus d. And my force, again, doesn't change. The signs don't change. It's still negative work. But the distance here is now just going to be D. Whatever that unknown thing is. My 80 and my 9.8 don't change. My 1,000 doesn't change. I still, jump out of the plane 1,000 feet. 1/2, 80, and now I can go in and put in 5 meters per second squared. So the unknown thing I'm solving for is D, and I could recycle my setup here because didn't change the forces that were in the problem. This is the power of conservation of energy. It's flexible like this. All right. 5 meters per second is a very sedate, like 8 miles an hour, something like that. Okay? Matter of fact, you won't break anything hitting the ground at like 10 to 15 miles an hour. Okay? If you've been trained on how to do it correctly, and well, I know in the military they train airborne infantry people to kind of crumple when they hit the ground. You keep your knees together, you bend them, you try to hit feet first and then roll to your side, okay, to lengthen out the impact. Getting ahead of ourselves, that's chapter 9. But it's very survivable. So we solved this for D, right? Is there some algebra to do here, isn't there? We got D in 2 different places, and so we got to factor some stuff out, all kinds of stuff. I'm not going to show you any of that. That's a math class. But the distance that the parachutist should have opened the parachute in order to hit the ground at a sedate 5 meters per second is, do we need a drum roll? Thank you. 206 meters. A 6 meter difference. Spelling the difference between life or death for these kinds of problems. Yes?
Is there a measure for like how much air resistance, like per meter?
Yeah.
It changes?
Yeah, there is. Okay. It involves differential equations. Okay. But in the military, okay, why would anybody jump out of an airplane and open their parachute at like the last minute? Okay. If you need to infiltrate an area and you want to do so undetected, okay, then you want to be able to open your parachute, which has this, it's big. It can be seen for quite a distance and seen also by radar, unless you coat it in special radar absorbing materials. But still, okay, pretty easy to see. Unless you can drop, say, into a valley and not open the parachute until you are below the mountains on either side of the valley. Okay? Very dangerous, but very doable. Here's a picture. Okay? This is a member of our military that is pulling off something called a high altitude, low opening training jump. And you will notice that there's something attached to this soldier. The dog. You see the dog? Tail over there, muzzle over there, okay? Yes, okay? Our special operations forces do train with animals. I know this. My mother is an animal trainer, not for the special forces. She does seeing eye dogs, but there's a lot of crossover there, believe it or not. And there are dogs in the military that do some fantastic things in defense of our country and our freedoms. But these high altitude, low opening jumpers, they're called halo jumpers. They kid because they say, well, if you do it wrong, you'll be wearing a halo. High altitude, low opening, they can jump out of airplanes at a classified height above the ground, okay? Usually in excess of 30,000 feet, like where standard airliners fly, okay? So that gets the airplane out of range of missiles, things like that. But then the parachutes don't open until very, very close to the ground. And it's not within human ability to judge the timing on these things. And so computers are put in charge of when these parachutes open, okay? And in doing so, right, our service members are putting their lives into the hands of very hopefully good computer programmers that have very few bugs in their software.
What's that line?
So that is called a drogue chute. It's a little miniature parachute that makes sure that the diver and its animal companion are oriented with their chests to the ground. Okay, it's providing friction to make sure that there isn't any tumbling going on, which can be bad when you have a dog strapped to your chest. Okay, and equipment and all those other things. There's some training videos I've seen where they're training these dogs to jump out of airplanes. Because let's face it, dogs are smarter than humans. They would not jump out of a perfectly good airplane unless they were told otherwise. Right? Okay. So in some cases, I've seen video where the dogs have oxygen masks. Right? Okay. I'm guessing in this, since it's a training jump, they just muzzled the dog. Okay, and didn't jump from very high. But they have these masks that go over the dog, and it looks exactly like you think it does. It looked like a dog wearing a gas mask, right? Okay, oxygen tube, the whole thing. And in the training videos I've seen, they put parachutes on the dogs, separate from the jumper. And the parachute has a little handle on the back, okay? And the handler will grab the dog by the handle, okay? And the dog is blinded, by the way, okay? The mask that they wear puts blinders on their eyes, again, because the dog's smart. It's not going to jump out of an airplane, right? Okay? They pick up the dog by the handle and they chuck it out the back of the airplane, okay? And then the service member runs after it, okay? And they jump together. They usually land far apart, but then they're trained to go and find each other and all that kind of stuff. So, absolutely amazing skill represented by our military. So, yes, halo jumping. Very definitely a thing, and much more precise calculations than the ones we did are required to make sure it gets pulled off correctly. I will see you tomorrow, where we will do halo jumping. No, we won't. We will do centripetal acceleration and maybe, just maybe, a field trip. We'll see.